My name is Frits de Mul and I would like to talk about integral types as needed in electromagnetism. This presentation is part of a series of presentations about topics of electromagnetism. We talk about multidimensional integrations, and it is integration of charge and currents over lines, planes and volumes. There are line integrals, surface integrals and volume integrals with examples. Why is that needed? Well, to perform integrations over volumes and surfaces, we have to rewrite the charges and the current elements, dq and di, into coordinate elements because only coordinate elements can be integrated spatially. And then we use charge and current densities. Now we will talk about the element itself and the integrations over 1, 2 and 3 dimensions. The current elements are dealt with in another presentation. First, line integrals, scalar. It is well known, of course, one-dimensional integrals. Is the meaning of f is the area under the curve. And an example, calculate the average temperature Tx between x1 and x2 is the integral of Tx dx divided by x2 minus x1. That's the average temperature. Scalar is multidimensional. Integration from P1 to P2, point 1, point 2, over a length dl. And the problem is then, which integration path do we need? In general, the results of the integration depend on the choice of the integration path. For instance, suppose we have a temperature field as a function of x and y is a constant times 2x plus y. And we have 2 points, P1 and P2. What is the integral over this temperature field? Different paths will lead to different results. Let's calculate the line integrals first and check. First, over path 1 is P1 to P2 is first integrate over the y coordinates, then integrate over the x coordinate, and you end up with 14 times c. The second path, the same type of integration, but now first over dx and then over dy, and this will lead to 16 times c. So that's different. And that is in general. When the result turns out to be independent of the path, we talk about conservative fields. A vectorial integral. The definition is integral over a path dl of a vector a is given by a dl times cosine theta, and this is the product, the scalar vector product of a and dl. And the L is along the integration path. An example, the work done by a force is the force times the path, is F times dl cosine theta integrated over the path. And if L is perpendicular to the L, if F is perpendicular to the L, then the work will be 0. And examples are centripetal forces or magnetic forces. Now the surface integral. Again the temperature field, C times 2x plus y. The problem is determine the average temperature over a certain surface. Find the formula and calculate. Well, the formula is, of course, integral of T over ds divided by the integral over the surface itself. And when we do that, we can perform the integration here, and the result is 5 times c. A vectorial integration over a vector field, then we need the normal unit vector on the surface, and that is parallel to ds, and ds is defined as the normal times the size of the surface element. And the definition of the vectorial surface integral is the surface integral of the vector times the normal, and that's a scalar in product, and it can be written as the normal vector times the value of the surface element, and in this case it will be the vector form times the cosine theta, and the cosine theta is the angle between the direction of the vector field, the local direction, and the normal vector on the surface. Example: suppose we have an area S in Z is 0 plane, and there the vector field A is x times Ex plus 2y times Ez plus 3 times Ey plus 3 times Ez. The normal vector is given here, and normal vector is parallel to ds at the surface. Well, we can perform the integrations here, dx dy cosine theta, and on the surface, on this surface in the xy plane, we can perform the integration dx dy, and we end up with 6. And there is only a contribution from the perpendicular component, and the perpendicular component is parallel to Ez and perpendicular to the xy plane. We have calculated the surface integral over x is 1 to 2 and y is 1 to 3. Now, a surface integral over a sphere. The surface element is du times dv. Du is r sine theta d phi. It's given here, r sine theta d phi. And dv is r d theta. And suppose we have a vector field B pointing outwards. And suppose B is given by r sine theta er plus cosine phi e theta plus tan theta e phi. Then calculate the surface integral of B over A at radius r over an octant. So theta is between 0 and pi over 2, and phi is also between 0 and pi over 2. The normal vector is En is Er everywhere, the normal vector on the surface. And then we can integrate this equation over theta and phi in the normal way. And here is the surface element. R squared sine theta d theta d phi is given here. And when you perform the integrations, you end up with an expression like this. The volume integral. That's, we only do the scalar form. And suppose we have a block V, and that's limited by points 1, 1, 1 and 2, 4, 5. It's given here. 1, 1, 1, 2, 4, 5. And let's assume that we have a charge density rho is C times 3x minus 2i plus 5z in coulomb per cubic meter. And determine the total charge Q in V. That we have a charge element dV is dx dy dz, and of course we can perform the integrations here, and we end up with 174 times C. Another example, spherical volume element. The volume element of that sphere is du dv dw. Du is r sine theta d phi. That's this one here, du. Here, this one, here. times the RD theta, that is this one here, this side, times dr, and that is this side. Suppose we have a charge density given by rho is 3 sine theta cosine phi in coulomb per cubic meters, and when you integrate over a certain region Q, in which r is between 2 and 3, theta between 0 and pi over 2, and phi between minus pi over 2 and plus pi over 2, then we end up with the integration over the region, and here is the integration, here is the volume element, and we end up with 195a divided by 4. And this is the end of this presentation.